Okay, so today we will have a review of several operations, and first of all we will start from introduction of our company. It will be a short introduction. Then we will proceed to three major questions. The first one is where user or engineer can find mechanisms of combustion of real fuel, single component or multi-component, and how the kinetic software can help in this. The second question, it is what kind of targets should we use or should we select to test our mechanisms with respect to different combustion processes which are encountered in the industry. And the third question will be related with practical needs in terms of the mechanism size and possibility to apply mechanisms of different sizes in the practical CFD simulations, and how the software, our software, can help to reduce mechanism size without loss of accuracy to adopt them for CFD simulations. A brief introduction about our company. We were founded in 2000 by scientists from Russian research institutes, and actually a lot of the specialists we have in our company, starting from quantum chemists and people in atomistic modeling up to gas dynamics and combustion process specialists. There are three main directions for our activity. It is inventive research, industrial and academic, and consulting of industrial companies. The second one is software development for chemistry-intensive modeling and design in complete cycle. And the third direction is customer support in their research activity using our tools and our expertise in different fields. In our company, we have developed a range of the software products which cover different applications and lie in different fields of the science. First of all, our product is a Chemical Workbench. It is integrated environment for development, reduction of the chemical mechanisms, as well as conceptual design of industrial processes. Chimera is a tool for calculation of the microscopic parameters of the reactions, for example, rate constants, and thermodynamic properties of the species based on the results of first principle calculations. The third software tool is the kinetic DB. It is a database for storing properties of species, chemical reactions, and all mechanisms, which is able to provide access to this data for range of the users which are working in the same lab, and actually the access can be provided even through the internet. The third tool is the MDTD tool. It's a tool for modeling the optical properties of metamaterials, and it is actually electromagnetic code. The next tool is the MD-KMC. It is integrated environment for atomistic modeling, which is based on molecular dynamics and Monte Carlo type simulations. And HLab is a tool for modeling and optimization of the MEMS elements fabrication. So let's go to our primary topic of this webinar. And first of all, let me just introduce the terms which we use and people in the combustion community usually use when they are talking about the kinetics of the combustion process and about the mechanisms of the combustion process. So people usually talk about the three types of the mechanism. The first one is the detailed kinetic mechanisms, which usually have about hundreds of species or even thousands of the species and thousands or several thousands of the reactions for hydrocarbon fuels. It is both for single component and multi-component. Usually it is supposed that these mechanisms work in a wide range of conditions. Nevertheless, it is recommended to test these mechanisms when we have new experimental data to see does this mechanism work well or not. The next type of the mechanisms, it is skeletal and reduced one, which usually include tens, maybe hundreds of species and tens and hundreds of the reactions. It is mostly typical for hydrocarbons fuel. Usually these mechanisms are derived from the detailed one, and when these mechanisms are derived, it is supposed that they should work for narrow range of the conditions and for specific problems. For example, it is ignition simulations or flame simulation or prediction of some type of the pollution, for example, NOx or unburned hydrocarbons or soot. And of course, it is recommended to test these mechanisms at designed range of the conditions. And the last one type of the mechanisms, it is global one, which usually contain several species and several reactions, and they are not derived from the all mentioned before mechanisms. It is and represents usually just a simple model of the process. The main disadvantage of this type of the mechanisms is that they can be applied in a very restricted range of the conditions and for only specific type of the problem, and they usually must be tested every time before application. Now the situation with the combustion mechanisms is the following. Usually if engineer or other industrial user or researcher in the academia would like to find the mechanism for his type of the fuel or for his type of the conditions, he needs to go to look through the original research papers. Usually it is for journals with supplementary materials, so where the mechanisms are described, where the mechanisms are provided as additional supplementary files to the paper itself. Also, there are a lot of the sources in the internet for these mechanisms. It is primarily the websites of the research groups, and in my presentation I cite only the websites with a lot of the mechanisms which are cover different hydrocarbons, hydrocarbons of the different complexity, and mostly it is sources for the detailed mechanisms. So among these links I would like to cite, first of all, it is a combustion chemistry group in the Lawrence Livermore National Lab, which provide a lot of the mechanisms, starting from the hydrogen chemistry up to C16, and both for pure and surrogate mixtures of the hydrocarbons. Another good source of the information, it is a website of the Combustion Chemistry Center at National University at Galway, which also provides mechanisms for pure hydrocarbons from C1 to C5, and also a source of recognized and well-known mechanisms. It is chemical reaction engineering and chemical kinetics groups in Politecnico di Milano, which provide extensive list of the mechanisms, both for small and large hydrocarbons. Particularly, these mechanisms contain reactions for nitrogen chemistry and polyaromatic hydrocarbons chemistry, and it is quite a useful source of the information for the simulations. So, in our company, we have developed tool which is called KinetecDB, so Kinetec database, in which we usually collect information about the combustion chemistry and chemistry of the non-equilibrium process in plasma. And this database is a convenient tool to organize all the mechanisms which you can find in the internet. So there are several peculiar features of our database, and currently we have put it into the database 53 mechanisms of hydrocarbon combustion. It is mostly from the open source literature with direct references to corresponding papers. This database is able to import the mechanisms from the widely used Chemkin format, and also it can export the mechanism into Chemkin format if you have put this mechanism manually into the database. Another feature which is important for engineers who are making the practical CFD simulations is that the database is able to export mechanism into format which is readable by major CFD codes and another kinetic simulation software. Also, the database have some specific features which simplify work with this database and data exchange between colleagues working in the same laboratory. Particularly, this database allows to provide access to data both from local and remote computers via internet. Also, users can extend content of the database by adding the mechanisms which they have found or developed and share these mechanisms with the colleagues. And finally, this database is tightly integrated with another software tools which are developed in our company. So now I will move to a short demonstration of the database and how it works and what is content in this database. So this is main window of the database. You see that there is a lot of the different types of the information here. First of all, it is a database of the substances, which include information about 6,000 substances, starting from the thermodynamic properties up to electronic properties of individual molecules, both in ground state and electronically excited states. It is first, and just as an example, I would like to show what kind of the information in terms of the thermodynamics. I have selected one type of the substance. We have its thermodynamic properties at standard conditions and approximations for polynomial approximations on dependence. These thermodynamic functions on temperature. And the information is provided in two types of the formats. It is NASA polynomial approximations and Russian-based Iftan polynomial approximation. Okay. The next type of the information, it is a processes database in which we are storing information about elementary reactions in different systems, starting from pure gas-phase systems where only thermal reactions can occur, up to reactions in non-equilibrium plasma and processes related with radiation of electronically excited or vibrationally excited substances. And the final part of the database, which is most important today for us, it is database of the different mechanisms which we have here. And what is important, it is that for every kinetic mechanism which is stored in the database, we have its name, we have a reference for this mechanism, and also you can see here a detailed list of the substances which are available in the mechanism and detailed list of the reactions. Now, when the mechanism is in the database, you can take a look on all species and species properties in this mechanism. So now I'm on the list of the substances for the mechanism. I can look through this list. I can go to some specific substance and look through its thermodynamic properties, its polynomial approximations, and make some conclusion. Does it fit my needs or not? Also, it's possible to make some plots of the thermodynamic properties. Their dependence on temperature. So it is dependence of the enthalpy of some selected substance. And I can plot and review this information for all substances in the mechanism. The same situation with the reactions. So here is the list of the reactions, and for every reaction we have identification what kind of the approximation is used for rate constant and what the parameters for this rate constant approximation. So, for practical needs, for everyday needs of the engineer, it is enough. Okay. The last thing which I would like to mention here again is that this database is coupled with other software tools of the kinetic, and mostly this tool is the Chemical Workbench. Okay, so now we have found a lot of the mechanisms for hydrocarbon, combustion of which we would like to simulate. The next question is how to test the mechanisms which we found and how to select the best one. So usually engineers in the practical CFD simulations investigate some specific processes in specific systems. For example, in industry, there are a lot of the applications where combustion takes place, and we can list just several ones. First of all, it is internal combustion engines, both spark-ignited and diesel. For this type of the system, one of the important combustion processes is ignition. For example, in diesel, it is essence of the diesel process, and in spark-ignited engines, the knock phenomenon is directly related with the ignition. The similar combustion process ignition is important in another industrial fields. For example, it is industrial safety, where explosions are investigated, and it is detonation applications, for example, in propulsion or simulation of the detonated coatings. Also, there is another type of the combustion processes, it is flames. And again, these flames are important both in the internal combustion engines, again in industrial safety where turbulent flames are a crucial phenomenon, in gas turbines, and in boilers applications. And the final phenomenon which is of interest for practical engineers is the determination of the formation of the pollutants in systems, for example, in combustion engines, in gas turbines, and in boilers. And this phenomena, I mean pollutants, is important in all applications which I have cited. And so now we have defined where our specific engineer is. So is he modeling internal combustion engines, then ignition and flame is important for him, or he is concentrated on the gas turbines, then the modeling the flame is important for him, or he is interested in the pollution control, then he needs to focus on the pollutants. And our task is to simulate this phenomena with good combustion mechanism. But what does good mean? So then, to answer the question, is the mechanism good or not, first of all, we need to identify how we will test this mechanism. So on this slide, I just have presented three types of the information which is important for us. First of all, combustion process which we would like to simulate with respect to our original system for CFD simulation. And the engineer should define will he model self-ignition or flames, laminar or turbulent one. Then for this type of the phenomena, people usually use some specific experimental methods to extract information which is directly related with chemical kinetics. So in the second column of the table, you see experimental setup. So here I have put information about experimental methods which are concentrated on investigation of the pure chemical kinetics effects with reduced effects of hydrodynamics or heat transfer, which is usually encountered in practical applications like engines, turbines, boilers, and so on. So in these experiments, people get information on the following quantities which we call experimental targets. It is for self-ignition, ignition delay time, and temporal for spatial profiles for temperature, stable species and radicals, and pollutants. Then for laminar flames, people usually extract information about laminar flame speed, extinction strain rate, or spatial profiles of temperature, stable and radical species. And for turbulent flame, people usually extract profiles of stable and radical species and pollutants. So now we have the following picture. We have original problem setup, related combustion process, and set of specific experimental targets which people get in specially designed experiments. And these experimental targets assure us that chemical kinetics have the primary input into these targets. So what we need to do is that we need to reproduce these experimental targets with our combustion mechanism. And the question how to do this. So on this slide, I'm showing the following information. Again, the combustion process, experimental setup which is used to extract information related with the chemical kinetics of the process, and the theoretical model which reproduces this experimental setup. So now I have the possibility to collect experimental data on ignition delay time, or flame speed, or species profiles, and put this data into the table. Also, I have a possibility to simulate the same experiments with theoretical models like calorimetric bomb reactor, or plug flow reactor, or flame speed model, with the different mechanisms which I have found in the internet. Then I will be able to compare the information obtained in the experiments and simulation and make conclusion which mechanism is good and which mechanism is not very good for my simulations. So for this task, our software tool, which is called Chemical Workbench, is designed, and there are several features of the software which allow to solve the mentioned task. So first of all, we have a full library of the reactor models which are designed to make kinetic simulations and to test mechanisms, particularly for combustion applications. So this tool is deeply integrated with KinetectDB, so you will be able to load the mechanism directly from the database and to run your simulations. Also, in our software, we have a capability to import external experimental data. So you, in the frame of the same software, you will be able to make a plot with calculated and experimental data simultaneously. Also, to cover a wide range of the parameters for which you can find a lot of the experiments, we have implemented the capability of parametric calculations. So you can put a lot of the values of temperature, for example, and run simulation in the batch mode. So the software automatically calculates desired parameters of the combustion process for different conditions and put on the same plot. The plots can be easily customized. Information from different calculations can be collected on the same plot, and also experimental data can be added to this plot. Also, what is important is that the plot can be automatically updated, so if you would like to extend the range of the conditions, for example, pressure or temperature for the simulation, then you can run the simulation, then go to plot, and it will be updated, so no need to again extract the data to put it there onto a specific table and then add plots like in Excel or Origin. So the software will do this itself. The final thing, which is very important for practical kinetic simulations related with the mechanism testing and validation, is the multi-core CPU support for massive parametric studies. So if you have a computer with a multi-core CPU, the software will use all the cores to run kinetic simulations in parallel. So you have a lot of the conditions to simulate, and the software automatically plans what will be simulated, when, and on which core. So it is possible to see significant acceleration of a lot of the simulations, and it really saves time when you need to compare several mechanisms in some range of the conditions. Okay, so now I will show some demonstration which we have presented. The example which we have, it is a comparison of the different kinetic mechanisms for methane auto-ignition. My goal is to test 7 mechanisms of methane combustion against data on ignition delay times, which are obtained mostly in the shock tube experiments. As I'm testing these mechanisms against data on ignition delay time, the most application for my system will be explosions, detonations, or dual fuel diesel engines, or dual fuel spark ignited engines. So now I have prepared the project in frame of the Chemical Workbench software, and we have already set up several calculations with the same input parameters by different mechanisms found in the internet. In one of these simulations, I have also loaded experimental data on ignition delay time for methane. So let me just review what kind of the input should be provided for simulation from the side of the user. First of all, we need to specify type of the problem which we would like to solve. The library of the reactor models is on the right side of window, and I will go to kinetic reactors, which are focused for our today webinar. These reactor models are designed for kinetic simulations, and combustion application is fits good for this reactors library. So colorimetric bomb reactor and plug flow reactors, it is 0 or 1D dimensional models which are designed to simulate specific experimental setups. For example, colorimetric bomb reactor is designed to simulate shock tube and rapid compression machine experiments. The plug flow reactor is designed to simulate the flow reactor experiments. Then flame reactors library is designed to simulate various experiments with laminar flames, and well-stirred reactors are designed to simulate jet-stirred reactor experiments. So in my particular case, I have a model of colorimetric bomb reactor which simulates the shock tube experiments. So the user should provide the following information. First of all, he should input the mechanism. In my first mechanism, it is a C1C3 San Diego mechanism, which was developed in University of California in San Diego. It is first type of the input. The second type of the input, it is a mixture composition for which I would like to simulate the ignition delay times. In my case, it is mixture of oxygen, argon as diluent, and methane. And range of the temperatures in which I would like to simulate the ignition delay time, it is actually the whole range, which can be specified as a set of the parameters in the following range from 900K up to 2200K. So actually I would like to run the parametric simulation with this specific mechanism. Also, for my simulation, I need to provide a lot of the another parameters which are related with the solver setup. It is calculation parameters, induction time calculation parameters, which mean that our software can automatically calculate ignition delay time and reaction time based on the kinetic curves. The only parameter which user should provide, it is a criteria for calculation of the ignition delay time. In my case, it is a maximum rate of the heat release, which is specified by parameter temperature. Similar thing is for reaction type calculation, and output parameters is just to specify solver how much points in time I should put in my final table. So the similar input is done for another mechanisms. In my case, it is a GRI mech. It is mechanism of Alexander Konov. It is mechanism from University of Leeds, mechanism of University of British Columbia, Eric Peterson, and the group from Italy, Professor Ranzi. So let's take a look on typical results of the simulations. First of all, I will go on to general results which are related with automatic calculation of the ignition delay time. So after the calculation, which I did just before the conference, the software have automatically identified ignition delay time for methane argon oxygen mixture in the range of the temperatures and put this information into the table automatically. The same results can be found in another calculations with another kinetic mechanisms. Also, I would like to pay your attention to experimental data. It is external information which we have loaded into our project, and we have collected a lot of the information, and as example, I give you just one set of the experimental data. So it is the range of the temperatures, reciprocal temperature, and the induction time measured in the seconds. So now let's go to the plot which compares predictions of the different mechanisms. So this plot setup put all the information about ignition delay times calculated with the different mechanisms and obtained in the experiments. So different curves represent different mechanisms which are provided in the legend here. And also we have experimental data of Walker put on the same plot. Let's go to plot setup to see the sources of the information. So on the bottom of this window we have a list of the curves from the plot, and now when you place the focus on some specific curve, then you can take a look which table is the source of the information. So I have induction time curve which is extracted from table of calculation with Peterson-Coulomb mechanism. If I will go to another curve, then we can see that the source of the information from the GRI MEC project. And the same, we can review all the results and all links between specific curve and specific calculation with the mechanism just looking through this list. So now we have a plot which can say what kind of the mechanism is bad and which mechanism is good for my specific conditions. For example, if I would like to simulate the ignition of the methane with oxygen at 1 atmosphere in the mixture which is diluted with argon, and the range of the temperatures should be between 2000 K and approximately 1000 and 500 K, then the best mechanism which fit my expectations would be this one. This is a mechanism of Peterson and Coulomb. And of course, I make this conclusion just visually review the results of the simulation. So now we have solved the task of testing the mechanism with the Chemical Workbench software and made some conclusions. So again, now we are engineers which have some specific problem for the CFD simulation. We have collected the different mechanisms and tested these mechanisms against relevant experimental data and have selected which mechanism fit our needs in the best way. Unfortunately, the most combustion mechanisms of real fuels, both single or multi-component, are very large. So on this plot, we show how the size of the mechanism of the single hydrocarbon component grows with number of carbon atoms in the molecule of the fuel. So it is seen that when you increase the number of carbon atoms up to 8, the size of the mechanism in terms of the reactions grows up to several thousands. And when you increase the size of the mechanism even more, then number of the reactions will be tens of the thousands. Of course, it is impossible to process these mechanisms with our current capabilities in terms of the CFD simulations. So even requirements of the memory do not allow us to run the simulations with the detailed mechanisms. That is why we need some tools to reduce mechanism complexity without losing its accuracy. To solve this problem, we have developed an additional tool which is supplementary with the Chemical Workbench software, which is called mechanism reduction model. There are several particular features of this software. And first of all, I would like to say that we have a library of state-of-the-art reduction algorithms, starting from the directed relation graph, computational singular perturbation, principal component analysis, and another algorithms may be not so well known, but also efficient in terms of the applications. This mechanism reduction model is tightly integrated with the chemical workbench. So it's possible to extract the results of the simulations with some specific mechanism, process this data with a mechanism reduction model, and then export mechanism back into the chemical workbench to run the comparison between original and reduced mechanism. So having this tool, you will be able to reduce the complexity of the mechanism. So I mean reduced number of species, reduced number of the reactions, without losing the accuracy if you specify what kind of the parameter you would like to simulate with the good accuracy. And now let me give example, a small example, how the mechanism reduction works with the chemical workbench. So before this session, I have prepared one echelon simulation in which I would like to simulate the combustion of the methane with GRI mechanism at conditions which you will see here. It is stoichiometric methane air mixture at 1,500 kelvins temperature. Also, this mixture is placed at conditions of 1 atmosphere, and I need to simulate the ignition delay time. So my target for the simulation, even for accurate simulation, is the ignition delay time. I guess that existing GRI mechanism is a detailed one to solve this problem, and I can reduce its complexity by removing redundant species and reactions. So what should I do with with Chemical Workbench software? First of all, I need to clone this echelon simulation. I just need to do copy and paste calculation in my project. So I got new calculation with absolutely the same set of simulation parameters and mechanisms. Now I will rename it and call reduced mechanism. So if we will go to this mechanism, for example, review the substances, we will see the typical list of the GRI-free mechanism, which includes 53 substances. The mixture is the same as in echelon simulation, and conditions of the simulation, I mean pressure, is the same. So what I should do now is I need to run this new calculation and to get the results. So the simulation is complete. I can review the kinetic curves from this simulation, so how temperature and species concentrations vary with time. Now I will make a plot to compare two predictions from echelon simulation and reduced mechanism simulation. I will go to its setup. Now I'm in echelon simulation. Select time and temperature to plot one curve. Now I will go to reduced mechanism simulation. Currently it is made with a full GRI mechanism, and select temperature and time, add new curve. So I have two plots. Now I will customize this to see the difference between curves after reduction. I should change scales. Now you see that predictions of two calculations coincide just because I used the same GRI mechanism as detailed one. But I would like to reduce the mechanism from the second simulation. To do this, I need to go to mechanism reduction module, which is encountered directly from the Chemical Workbench. So in a new window which appears, we have a full list of the reactions which are present in the mechanism. Now it is 325 reactions and the full list of the substances. Now it is 53 species. And I would like to reduce this mechanism based on information from the simulation. The method which I would like to use, it is directed relation graph method, for which I need to provide what kind of the species are of primary importance for me. And I would like to select that it is oxidizer, oxygen, it is water, it is methane, and combustion products like CO, CO2. And of course I need to mark nitrogen as diluent because it should be preserved in my mechanism to put it into the CFD for further simulations. Now I would like to specify the method parameter, which I think should be 1.2. It is my guess. And select that all time moments for the simulation are important for mechanism reduction. Then when I have set up all the parameters, I can run the process, and you see that after simulation, after processing the results of the kinetic simulation, I got mechanism with some reactions switched off. You see here that the reaction is switched off. I can look through the mechanism. I can look through the species in the reduced mechanism. And now I can put this mechanism back into the Chemical Workbench by pressing Save button. It asks me, should I replace detailed with the reduced mechanism? And I say yes. And now it is in the Chemical Workbench. Let me show that it is really reduced mechanism. I will go to list of the substances, and now it is only 37 substances, not 53 as in the original mechanism. So let's test the reduced mechanism and compare with the detailed one. Just run the simulation. Now the simulation is complete, and I go to plot. It is updated automatically. So it was original detailed mechanism, and now it is reduced mechanism. If you think that this deviation after mechanism reduction is acceptable for you, you can say that the problem is solved. You can review the final mechanism, take a look onto the substances, take a look onto the reactions, and put this mechanism into the database. So let's take a look on the reactions. It is really much less reactions in comparison with the original detailed one mechanism. And now I can put this mechanism into the database by pressing Save to Database. But also I can do similar save into the XML file and into the Chemkin file to put this information further in CFD simulation tools like ANSYS Fluent, ANSYS CFX, or similar stuff. But what if the accuracy of reduced mechanism is not acceptable? For example, you think that it is too large discrepancy. Then I need to repeat what I did before. So I need to clear the reduced mechanism. I need to again insert the detailed mechanism into my simulation. and then make the same operations which I have shown before. So run simulation, run a reduction procedure with different value of the reduction parameter or another type of the method, and now you will be able to get reduced mechanism of the acceptable accuracy. So to summarize what we have presented, it is the following. First of all, we have shown that the practical needs of the industrial engineer is to get information about how the accurate mechanism of combustion of the selected hydrocarbon fuel and how to reduce its complexity to put into the CFD. And there are 3 steps which can be solved with the tools which we are developing. First of all, you can search for your mechanisms in the literature or in the internet and put all the mechanisms in the database. So you will keep all the results of your search into the same place. And also you can share this information with your colleagues. And this can be done with the kinetic DB software. The next step is to evaluate the accuracy of the existing mechanisms against experimental targets. The set of targets is specific for the problem which you would like to simulate. And for example, for diesel engines, first of all, it should be ignition delay times. For detonation, it should be ignition delay times. And for turbulent flames in gas turbines, probably it should be laminar flames or turbulent flames. And the Chemical Workbench software can be used to put experimental targets which you can find in the literature or ask colleagues, like ignition delay times. And the same quantities can be calculated with the set of reactor models which are available in the Chemical Workbench. And the final step which you can do to make practical CFD simulations with the combustion mechanisms is to reduce your detailed mechanism by removing substances and removing reactions without losing accuracy. And the source of the information about required accuracy, of course, but you have all the tools which allow you to make conclusion. Does this degree of the reduction enough in terms of the accuracy or mechanism size or not? And now with the IntactDB, Chemical Workbench software, and mechanism reduction tool, you are able to solve all these tasks which we have reduced today. So our webinar session goes to end, and I would like to say that you can take a look on our software by requesting evaluation version of the software. Just email us. Also, we are ready to answer your technical questions just after this session. You can put your questions into the dialog box of the window. And also, if it is not preferable for you, you can write us technical questions on email, and we continue some specific discussions you would like. So thank you very much, and now we are open for questions. And ready to answer.